In section 11.3, we are going to learn one of the two ways that we will be able to multiply vectors together. And in this section, we are going to learn about the dot product. You may also hear the dot product referred to as the inner product or the scalar product. And this is just a type of multiplication that can be performed between two vectors that results in a scalar. So our result is not going to be another vector. We're just going to get a single number scalar answer back when we calculate dot product. So the algebraic definition that just involves some simple algebraic operations. If we have two vectors in component form, so we've got vector v equals v sub 1 v sub 2 and vector w equals w sub 1 w sub 2, then the way that we calculate dot product is by multiplying corresponding components. So we're going to do v1 times w1 and then v2 times w2 and then add those two products together. So there are no diamond brackets on our answer because this answer is not a vector. It's just going to be a number. And if our vectors were three-dimensional vectors, then they would also have a v sub 3 and a w sub 3, and we just follow the same pattern that we already see. We would just say plus also v sub 3 w sub 3. So we would just find that product as well and add it into our result. There are a few important properties for dot product, and they're basically just algebraic properties that we see with just normal numbers. So let u, v, and w be vectors, and let c be a scalar. So just a regular old number. Then u dotted with v will always give you the same result as v dotted with u. So the order of the vectors when you're doing the dot product does not matter. And this is called the commutative property. And the reason this works is because both of the operations that we're using to do this calculation are both commutative as well. The order that we multiply components in doesn't matter. They would be the same result. And then the order that we add these products in wouldn't matter. We'd get the same result. So the overall dot product itself is also commutative. It is also distributive. If you want to calculate u dotted with v plus w, we can take the u and distribute it if that for some reason would be easier for us to do. And we could say this is u dotted with v plus u dotted with w. And this is our distributive property. If we had a scalar multiplied by a dot product, even though we think of these as different types of multiplication, the fact that they are all multiplication allows us to again use the associative and the commutative property, and we could really multiply these in any way that we wanted to. So if we wanted to, we could calculate the scalar multiple of u and then dot it with v, or we can find the scalar multiple of v and dot it with u. And no matter what way we organize those multiplications, we would still get the same answer. We also have a zero element in our collection of vectors. So if we try to do a dot product between 0 and any vector, 0 just means we have a vector that has all 0 components. We will always get 0 because we know anytime we multiply by 0, those individual products will be 0, and then we add a bunch of zeros together, we get 0. So dotting any vector with 0 will result in 0. And then also, if you dot a vector with itself, you will see that the result comes out to be exactly the same as the magnitude of that vector squared. And I've got an example for us to do so we can take a look at that. So let's try a couple of examples. We are going to use vector r, which has components 5, -2, vector s has components 0, 3, and vector t has components -1, 1, and we're going to do a bunch of different calculations. First, we want to do r dotted with t. So that means we need to multiply corresponding components. So the first component of r is 5. The first component of t is -1. The second component of r is -2. The second component of t is +1. And then add these results together. So we get -5 plus -2, which means our dot product is -7. And notice that it just came out to be a scalar, not a vector. For the next one, we want to do r dotted with t times s. Well, we've already calculated r dot t to be -7. So this is the same as -7 times s. And that's really just a scalar multiplication. So all we have to do is distribute -7 into the components of our s vector. So we're going to do -7 scalar multiplied with 0, 3. And we'll do -7 times 0, -7 times 3. We get 0, -21. For the next one, we have 2 vector r dotted with vector t. This goes back to property number 3 that tells us we are really allowed to do those multiplications in any order that we want to. And since we already have r dot t, we could think of this as 2 times -7, which is -14. And if you want to, try to calculate that in a different order and see if you get the same thing. Calculate 2r and then dot it with t. 2r would be 10 -4. And then if we dot that with our t, that means we need to multiply corresponding components. We'll get -10 plus -4, which is, like we expect it to be, the same exact result we got before, which was -14. One more quick example. We want to do s dotted with s. So we want to do a dot product between a vector and itself. And that just means we're going to do 0, 3 dotted with 0, 3. So we multiply first components. We have 0 times 0. Multiply second components. We have 3 times 3. And we get 9. And this is also exactly the same as what we would have gotten if we just did the magnitude of r and squared it. The magnitude of r, remember, is its first component squared plus its second component squared. And it says if we square that, we should get the same thing. On the inside, we've got square root of 9, but then we're squaring it, so the square and the square root cancel each other out, and we do get the exact same result. And let me fix one thing here. This is vector s. Yeah. So when we calculate s dot s, we get 9. If we also just did the magnitude of s and square it, we also get 9. So whichever calculation is easier, as long as we know that they're equivalent, we have our choice of which one we want to do, and we should get the same answer. So dot product is a fairly easy calculation, but dot product all by itself doesn't tell us a whole lot about what's going on between these two vectors. Dot product is more of a helper for a lot of other calculations. So we also have a geometric definition, and this doesn't use the vector components. Instead, it uses their magnitude and direction. So you could also calculate a dot product, v dot w, by multiplying together the magnitude of v, the magnitude of w, and the cosine of theta, where theta is the angle between those two vectors. We don't typically calculate dot product in this way, but this formula, if we manipulate it just a little bit, we can rearrange it so that it gives us a formula to calculate the angle between two vectors if we have those vectors in component form. So I'm going to isolate the cosine theta here, and to do that I'll have to divide over those two magnitudes. And what we get is cosine of theta is v dot w divided by the magnitude of v times the magnitude of w. So if we've got v and w in component form, we could easily calculate the right-hand side of this equation and then ask our calculator what cosine inverse of that value is, and it will tell us the angle between v and w. Now typically, if you think about two vectors in standard position, let's say this is v, and let's say this is w. There's technically two angles between these vectors. There's one clockwise angle, counterclockwise angle, and then there's one clockwise angle. And our calculation here is always going to give us the smaller of these two. So it would give us the red one. If we wanted the other angle for some reason, all we would have to do is subtract 360, because the red angle and the blue angle here always add up to 360. So if we did our calculation with our formula, we could get that smaller red angle, but if we want the blue angle, we just subtract from 360 to get the blue angle. And this formula leads us to a really important rule about determining whether two vectors are orthogonal. And if you've never heard the word orthogonal before, it means exactly the same thing as perpendicular. And perpendicular is when two things have a 90-degree angle between them. And another term that you'll see throughout this semester is the word normal. And all three of those, orthogonal, perpendicular, normal, they mean the same thing. They mean our two vectors come together at a 90-degree angle. Well, cosine is 0. The cosine of 90, or pi over 2, depending on whether we're in radians or degrees, the cosine of a 90-degree angle is 0. So if we knew they were at a 90-degree angle, the left-hand side of our equation here should come out to be 0. On the right-hand side of the equation, we have a fraction, but the only time a fraction will result in 0 is when the numerator equals 0. So this means that we can prove two vectors are perpendicular to one another if their dot product is 0. So let's try a couple of examples with these angles. First, we're going to do a geometric dot product, and then we're going to calculate an angle. So we want to find r dot t if the magnitude of r is 5, the magnitude of t is 12, and the angle between r and t is 60 degrees. So the geometric formula for dot product says we just have to multiply together the magnitude of r, the magnitude of t, and then the cosine of the angle between them. And we know all of those values. The magnitude of r is 5, the magnitude of t is 12, and the angle between them is 60 degrees. So 5 times 12 is 60, and then the cosine of 60 degrees is a half. So 60 times 1/2 is 30. So again, remember, our goal here was to calculate a dot product. Another word for dot product is scalar product. That's because the answer that we get in the end is just a scalar. One more example really quick. We want to find the angle between vectors m, which has components 2, -3, 6. So this is a 3-dimensional vector, and vector n, which has components 0, 5, -1. So remember earlier when we said if you have 3-dimensional vectors, you just follow the same pattern for that third component. The way that we can find an angle is by manipulating that geometric formula for dot product. And we end up with cosine of theta, which is the angle between our two vectors, can be found by doing the dot product of the vectors and dividing by the magnitude of the vectors. So in our numerator, we want to do the dot product. We're going to multiply corresponding components. So 2 times 0 plus -3 times 5 plus 6 times -1, and then divide that by their magnitudes. So the magnitude of vector m is 2 squared plus -3 squared plus 6 squared. And the magnitude of vector n is the square root of 0 squared plus 5 squared plus -1 squared. And you don't have to write all of this out in one formula. You can just calculate these little pieces individually, and once you have them individually, throw them back into the formula. That works just as fine as well. So 2 times 0 is 0. -3 times 5 is -15. 6 times -1 is -6. In the denominator for our magnitudes, we're going to get 4 plus 9 plus 36, which is 49. And then we're also going to have 0 squared and 5 squared and 1 squared, which is square root 26. So we've got -21 divided by, and I'm going to show you a little trick that will make this a lot easier to put in the calculator. Since both of those factors in the bottom are under a square root, we can really put them under one big square root and say it's the square root of 49 times 26. Now this is what cosine of the angle is equal to. So for us to actually calculate the angle, we're going to have to ask our calculator what cosine inverse of -21 over the square root of 49 times 26 is. And I'm just going to do this in degree mode to get an answer for my angle in degrees. And I get about 126 degrees. So just to kind of drive this home a little more, the way that you can think of this, and this one is a little tricky to draw because we're in 3 dimensions, but if we have these 3-dimensional vectors, here's our x-axis, our y-axis, and our z-axis. Vector m has components 2, -3, 6, which means we come out 2 on the x-axis, -3 in the y-axis, and then 6 in the z-axis. So there's vector m. And then vector n has components 0, 5, -1. So we're not going to move it all on the x-axis. We're going to go 5 units on the y-axis, and then down 1 unit on the z-axis, which is going to put us about here. So what we've just calculated is the angle between these two vectors, and it always gives us the smaller one. So we're not following any particular plane here. We're not going around the xy plane or the yz plane. We're finding the shortest distance that will rotate us from vector m to vector n. There's another angle if we go around the back way, but that's a much bigger angle. And if we wanted that angle, we would just have to subtract from 360. And we would get 234 degrees. But typically, all we care about is the angle that we get directly from that formula.